The purpose of this video is to help students to understand some kinetics mechanism problems in chemical kinetics. It is true that from the imagined reaction mechanism, we could write a rate law. It's also true that from a rate law, we can imagine or hypothesize a reaction mechanism because it will help us to focus on the rate determining step. Let's look at a particular reaction, and we need to remind ourselves that this reaction between nitrogen dioxide and carbon monoxide, you cannot look at the stoichiometry and infer the reaction mechanism. You might think, for instance, that the carbon monoxide molecule runs into the nitrogen dioxide to trigger the rearrangement. But in fact, that's not true. If the fundamental starting process were carbon monoxide colliding with nitrogen dioxide, then if we raised the partial pressure of either gas, it would affect the rate of the chemical reaction. However, only the pressure of the nitrogen dioxide affects the rate of the reaction. You can change the carbon monoxide pressure, but it will not affect the rate of the chemical reaction. Only changing the nitrogen dioxide does so. So that means that a collision between carbon monoxide and nitrogen dioxide is not the slow step in this reaction. This is a reaction mechanism that's postulated in order to recognize the elimination of carbon monoxide from the mechanism. You'll notice that the first step is a collision between two nitrogen dioxide molecules. Since only when the nitrogen dioxide pressure changes do we see a rate change, the rate law then would only have the nitrogen dioxide concentration in it. It would not have the carbon monoxide in it. And because of that, we believe that there is a collision between two nitrogen dioxide molecules that is the slow or rate determining step. And so we look at the experiments that are done, and we find that in fact that's true. The rate law is rate equals K times the concentration or partial pressure of the nitrogen dioxide squared. Now most of the time we start with an overall reaction and the data needed to produce a rate law. In this case, we see that the nitrogen dioxide pressure change will increase or decrease the reaction rate, and so we write the rate equals to K times, in this case, the nitrogen dioxide partial pressure squared. But from this information we could infer that carbon monoxide is not involved in the slow step, but that to set up the reaction, two nitrogen dioxide molecules must be colliding. And that's of course what we need to begin writing a reaction mechanism. Let's look at another reaction. What would be the rate law associated with this series of elementary processes? Now the first step reacts acetone here on the left with hydrogen ions, shown in the form of hydronium ions, to form a protonated acetone molecule. You can see that the first step, the hydrogen ion, is put onto the oxygen, which originally was double bonded in the acetone, and now of course this has a plus charge that was brought in by the hydrogen ion. If you draw the Lewis structure a little more carefully, you'll see that that's true. The water, which was actually having one water on a hydrogen ion, is fictional. Hydrogen ions are surrounded by many water molecules, but this shows the acid-base reaction according to the Bronsted-Lowry theory. This is postulated to be a fast equilibrium, which sets up the next step in which the protonated acetone reacts with water, and the water strips the hydrogen ion away from the protonated acetone, leaving an intermediate. And here the intermediate, which has a double bond between these two carbons, reacts with the water to form a second intermediate, and that of course releases the hydrogen ion back into the water. Then the final step is a reaction with the bromine, which, as you can tell, is not involved in the slow step and so would not appear in the rate law. If this second step is the slow step, as we see here, we should find that the rate is dependent on only two things other than the presence of water. It would depend on the concentration of the acetone. That, of course, is going to be important because it sets up this equilibrium that is necessary for the second slow step. It should also depend on the concentration of the hydrogen ion, and of course we measured that by the pH of the solution in which it is happening. So we should see this rate law. Rate is equal to some kinetics constant times the concentration of the acetone times the concentration of the hydrogen ion. There's one more thing to note. The hydrogen ion is used in the first step here on top, and it is recovered back in the second step. It's necessary for the reaction, but it's not changed. If something speeds up a chemical reaction and is not permanently changed, it is acting as a catalyst for the reaction in question. Remember, for the concentration of a species to appear in a rate law, that is, for that concentration to affect the rate of the chemical reaction, it has to appear either in the slow step of the mechanism or in some elementary reaction that precedes the slow step. Either one is possible, and either one can give us a species that would appear in the rate law.